derivative, and it takes these different values for the error by getting the original error, its past error by integrating it, and its potential future error by deriving it. And with that, it adds them all together to try and figure out where the robot will align, where the robot can align itself to like a desired point. And with that, it required a lot of fine tuning of parameters just to actually get it to work. And I was just really proud of helping get that work.
I think one thing I was very proud of doing was the April tag detection, because it helped me learn so much more about using a camera to look through what it's seeing and detect like as April tag, and learning how to have the robot angle itself and move towards that direction as well.
April tags was also another thing that I was really proud of. As you can see in the video behind me, yeah. So our code is highlighting and following the April tag, and I thought that was really cool. I always wondered how QR codes work, and April tags are very similar to QR codes, as you can see, and I just thought that was something really cool that we integrated into our project.
I was really proud. I'd like to turn this in a new direction. I was really proud about our group's efficiency with regards to our preparations. Because we had such limited time, we tried to maximize our output in the pool. So in order to do that, we had to really get in between the hours all of our code ready, and that took a lot of just trial and error, but we got it done.
I think for me, the most challenging part and my favorite part was the lane detection. Can you go to the videos? So the first one. Yeah, so lane detection was something that at first I looked at it and I thought, there's no way that's gonna happen. Like, we're not gonna get the lanes to be able to get detected, but ultimately I wrote a lot of code and then I learned a lot about how computer vision works. And so you can see in those videos that it is successfully detecting the lanes using a ton of steps of post-processing and being able to math and selecting lanes and a ton of other stuff, and using that it's able to actually detect a lane, which is something that I thought was not going to be possible, and ultimately we were able to do it. So I thought that's cool.
Yeah, definitely. I think you guys all touched on some great points, whether it was technical or interpersonal. You guys certainly faced and overcame a lot of very unique challenges that I don't think many people your age really encounter. So I just want to say, first off, congratulations for persevering and making it to the end of the course. And I hope you guys have a wonderful time here at the BWSI final event. Thank you so much.
Thank you.
Obviously, this course has a lot of unique challenges. What was something that happened during the course that you found really challenging, and how you as a team kind of came together to overcome that? Do any of you guys have an example of that? Yeah, you want to go?
All right. So you may have heard this from other teams in the AUV course, but one thing that we really didn't like was the amount of pool time that we had. Yep. And so as a result, a lot of us, we had to come early at 7. We had to arrive at MIT at 7. So every morning for the past 3 days, I think a lot of us have been waking up extra early, some even at 5 a.m. And we all kind of came together and we support each other by giving tips on code, giving tips on how we could make the robot actually work because of our limited pool time. And so we had to pool our experiences and testing together.
Yeah, and as one of our previous listeners also mentioned, that the PID tuning, which is the proportional integral derivative control, was a hard time, since we have 3 different robots, and each of them, they're all kind of different and used for there might be a little bit rusty on each of them, and it was sort of a different level of them. So each of the motor, their sensitivity, how much they give them the power at 100%, they're all different for each of them. So each of them have the different PID value. So every time we have to, before we actually run our code, we always do the tune for them. Yeah.
Thank you so much for sharing. I think this is my last question to you guys. What was your personal highlight about the course for BWSI?
First off, It's definitely our professor, Dr. Saad. He is one of the most charismatic person we have ever met, and he taught things in a way that we all understand. And he's always making sure every student is on their track and just always on the work and on the grind.
And I'm sorry, I'm probably gonna steal some of your highlights too. Our TAs, we have three very awesome TA. Three very awesome TA. Especially one that helped us the most is a TA called Ashjad. He was super humorous, super funny, and helped us a lot in the way. And like the people in here are just really amazing, and that's definitely one of my highlights.
I think my highlight was probably just meeting fellow like-minded people as well as our TAs and professors. You know, we've had like a lot of like class bonding experiences. Like we had a game day, we played basically Fall Guys together, and yeah.
For me personally, before I filled out the application for this program, I didn't know anything about programming or Python or C++ or GitHub or anything. So it was really a challenge for me to keep up with the coursework in this program. But after I was able to learn with the challenging pace of this course, I'm really able to understand things at a rate that I didn't know was possible for me before. And also, as other people mentioned, I think meeting the people here at BWorks was really one of my highlights.
All right, since a lot of my teammates have been talking about people, I'm going to talk more about the experiences I had. So while the AUV course didn't really go to seminar often because that was during our pool time, the little pool time that we had, I really liked it when people came into our classroom to talk to us. So for example, there were these two Navy officers that came in and they explained how their submarine that they had been stationed on was working. And I really found that interesting, and I loved having them here.
All right, thank you so much for sharing, guys. I really appreciated hearing about all of your unique experiences through the past 4 weeks. I'm glad that I was here to watch you all persevere through all these unique challenges that you had to overcome. I just wanted to say congratulations for making it to the final event. I hope you enjoy the rest of your day. Thank you so much. And we're back with our third group from the Autonomous Underwater Vehicles course. It looks like they want us to show us their presentation in full. Would you mind introducing yourselves to our viewers at home?
Hello, I'm Kevin, yeah.
Hey, I'm Srutwapala.
Hello, I'm Kevin Wu.
Hi, I'm Vismay.
And I'm Keshav.
So what do you guys have to show us today?
We have quite a lot of things to show you. So we're the Autonomous Underwater Vehicle Challenge, and we're the Argonauts. And so first I want to talk about some major tools we use, and I also want to talk a bit about our professors and our TAs. So first, with the major tools that we used, they introduced us to Python. Python was sort of the main programming language we used to code our ROV, and we also used it to simulate a bunch of physics as well. Blue Robotics, that's the actual manufacturer of our ROV, and they also created some of the main code that goes along with it that was sort of running in the back end. Q Ground Control, that's sort of like a 2D simulation which we use in order to model our ROV before actually testing in the pool because we had such limited pool time. Finally, Raspberry Pis and C++. With the Raspberry Pis at the beginning of the course, each of us were given Raspberry Pis. We sort of did all our work there, so we were all working on sort of the same interface, and it was a lot easier to work together as well. With C++, we used that at the beginning. That was one of our beginning software languages that we used. And it was sort of used to learn about optimization of code and stuff like that.
I also want to add that we didn't have enough time to put on the slides because it was only in the last 2 days. But we also used Gazebo as a 3D simulator. But we only got it, working in the last 2 days.
Okay, so now I want to talk a little bit about our course and sort of what we went through. So, we're the Argonauts, and our ROVs, we love our ROVs. They're Nemo and Dory. They're very dear to us. And the objective of this course was to eventually, these are all ROVs right here. And so ROV stands for Remote Operated Vehicle, which means it's sort of using an Xbox controller, you can sort of control this thing, make it move forward, backwards, up, sideways, and do all sorts of tricks. But what we wanted to do was to make it automated. And by that, I mean, at the front here, if you sort of flip it, you can see on the sort of inside, there's a Raspberry Pi. So what we wanted to do was we wanted to swap this Raspberry Pi with our very own in order to automate it and run our own software. So now I want to talk about our final project. So leading up to the end, what we really wanted to do was to do a predator-prey simulation. So one robot would be the predator. This predator would be tracking down the prey and trying to catch up to it. And it would sort of do this using different detection algorithms to try and find where it is, find where its own position is in relation to the prey and move towards it. The other role is the prey. The prey's goal is to run away from the predator and get as far away as possible and sort of outlast the predator. And so with this program, typically you find a lot of underwater vehicles and even how some animals use like echolocation and stuff like that, and underwater vehicles use sonar. What we had was we had a camera and we had an IMU, and those were the main sensors we used in order to detect the ROV and its current positions.
So this is our first week. In our first week, we learned about Python. We learned the fundamentals of Python as well as how to use unit tests to test our code. And then we also learned about how to use matplotlib to plot our physics and functions into Python. And then we also learned about how to apply NumPy array and then multiply matrices. And then we also use calculus to find the ROV speed and position using integration and derivatives. And you can see this is the position versus time graph with respect to the ROV's position in the pool. And then this is all the physics that we've done in order to calculate the net force generated by all 6 thrusters. So we have 2 thrusters that's capable of moving the robot up and down, and then we have 4 thrusters that can move the robot like pretty much any like directions. It can move forward, backwards, and then roll, pitch, yaw, like all that kind of stuff. So for physics right here, we multiplied the forces generated by the X components and then the forces generated by the Y components with the rotational matrix. With that, we're able to find the net force generated by the ROV. So yeah, here's a calculation. And we were also able to use NumPy array to do the calculation on Python as well. And that is our second week. During our second week, we went to the MIT Sailing Pavilion trip, where we used closed loop control, and then we basically also tested the lights and the camera in the Charles River. So as you can see, yeah. So these 4 are the lights of the ROV, and then the camera is right in front of the ROV. So yeah, we basically just tested those in the Charles River. Yeah. And then we were also able to use all the physics and math that we learned during the first 2 weeks to make a dance template. Basically, we use that, and then the ROV is going to execute like a series of motions in the pool. So as you can see, these are basically all the commands the ROV is going to execute. And then we have a video right here. Wait, how do you do this? Oh, okay, yeah. So that's a simulation.
Can you explain what it's doing?
Yeah, so right now it's going up and down, and then that's moving forward, and then now it's figure 8.
So it's like a simulation that's automated.
Also wanted to say that this was a learning experience for us, because for this we had to calculate, if we wanted to go forward, we had to calculate how much power to send to each of the motors. And we had to do this for every single one, even for a donut and reverse donut. So it gets really complicated really quickly. So it didn't turn out very well because it like just got so complicated and confusing that, yeah, it was just really difficult.
So then moving on to week 3.
Whoopsies. Okay, so at the first part of week 3, we made a chat bot or a chat app. And in order to do this, we learned about UDP and TCP. And then we also learned about clients and servers. We used Netcat to create a connection between a computer and a server. And then the computer would send text or whatever through terminal into the computer, and then the computer would send it out to all the other people connected to the server. So in the end, we created something similar to Discord or iMessages so that we can send things to each other. The end goal for this was to, and we actually did this at the end, was to have one client send a command to a server, and then that server would send it to the ROV, and it would make the ROV go forward or backward or whatever. I also want to mention that the command it sends to the server is still in power to individual motors, so it was still not what we wanted to do. Oh, and this is a demo. The video is really long, so we might want to skip through it, but basically what we're doing here is this is the client view. The client is entering a username and a password. And as you can see here, Visme is sending a message and has sent it to the client and also sent it to the server. And then Keshav is typing his messages and stuff. Okay.
So to control the robot, we had to first learn about PID control. And this way, instead of just supplying raw powers to each of the motors, we can control it in a smart manner using giving it a desired position. And then the robot itself will figure out how it can get to that position without us telling it what to do. So PID stands for proportion in integral derivative control. So these three components allow us to determine what power we need supplied to the motors to get it to where the ROV wants to go. So the proportional term will essentially determine the magnitude of the power based on how far away from the desired position the robot is. So if it's really close, it's going to move really slowly, but if it's far away, it's going to move quick so that it can get there in time. The derivative component, that determines how fast the motors run based on how quickly the air is changing. So as you get closer to where you want to go, you want to slow your ROV down so it doesn't overshoot. And this is what the derivative term allows for. And then the integral term, that accounts for error that accumulates over time. So let's say you stop the ROV around 1 meter away from your desired position. It's going to realize that it's not at where it wants to be. So as that error accumulates, it'll move slowly towards its desired position and end up where you want it to go. And so we use the IMU, the inertial measurement unit, on the AUV itself. And this has 9 degrees of freedom. So it has compasses, gyroscopes, and also measures translational motion as well. And we also had to create an error wrapping function so that the robot would wouldn't turn all the way around each time. So let's say you're moving from -2 degrees to 2 degrees. You wouldn't want the robot to turn 356 degrees all the way around. You want it to go the shortest path, which is the 4 degrees. So we'd have to wrap the error so that it wouldn't always go in one direction. It would go whichever way is the fastest.
Yeah, okay, so Visme kind of already covered a little bit of this, but so the next step was to do heading and depth control. So for depth control, we use the PID to, what we would do was we would have our computer, we would input depth we wanted it to go to, and then we would use the PID to control the ROV to go down to that specific depth. The input would be the error in meters. So at the back, it has a pressure sensor. Or depth pressure sensor, and it uses that to calculate depth. And then from there, it would calculate the error between its current position and where it wants to be. And then its output would be the power to the motors. And for heading, yeah, Visme already talked about this a little bit, but we want it to go to the certain heading we want by calculating the current heading minus where we want it to be. And yeah, we also...
So one of the tasks that we had to do was detect lanes in the pool itself. And so to do this, we used an algorithm called the Hoff line transform, which essentially gets all of the lines in an image based on a certain mathematical algorithm. And then so once we had all of these lines from the edges, we would then determine which ones constituted lanes based on the difference in the x-intercepts as well as the slopes. So whichever ones were close together and had around the same slope would be paired into lanes. And then to figure out the center lane, we would figure out which pair of lines is close to the center, and we'd mark that as a center lane. And we'd combine this with PID control to follow the lanes and maintain a heading that is perpendicular to parallel to the lane and follow it straight down the pool.
Okay, so in terms of actually going back to the predator versus prey challenge, how we're actually going to track another ROV, for that we're using April tags. So these are April tags right here. they're fiducial markers that have a very distinguishable pattern that allows you to very easily determine where they are relative to the camera. So as you can see, we also have them on the ROV. So these April tags are used for pose estimation and determining the position of the ROV or like any vehicle relative to the tag. So because of their pattern, if you know their size, as you can see in the image here, we're able to determine translationally how far away the April tag is from the center of the camera, and we can use that to calculate how far we need to move in each direction in order to reach the tag. And we can also find the rotational orientation of the April tag by using, again, the size of the pattern, which also tells us how far away it is longitudinally. So we can use all of that information to determine exactly where the April tag is relative to the ROV. And then we can sort of track the April tag using the various forms of control that we mentioned earlier with PID control to control the heading, longitudinal and lateral movement. So we basically learn how to detect the tag using a library for detecting April tags, and then essentially follow the April tag, which is going to be in an ROV, in order to like be the predator and sort of follow the other ROV. So on the next few slides, we have some demos of this detection working. So as you can see here, this is in the swimming pool. The text is kind of covering the video, but essentially that's the output to the motors for the robot to track the April tag. So as you can see, we have a center crosshair, which represents the center of the camera, and then a crosshair on the actual April tag, which represents the position we want to get the ROV to. And then the green outline just indicates the detected April tag. So as you can see, the crosshair, the center of the camera, was following the April tag in order to align itself with the April tag. And then here is a video of us tracking the April tag. There's somebody or me holding the April tag in the pool, and you can see the ROV sort of following it. So as the April tag's moving away, the robot's following it because it's using the orientation of the April tag to determine where it is relative to the April tag, and then it's moving towards it. And we were just kind of coaxing it back to the end of the pool to take it out of the water. But this is just we also have with that group over there, actually we tested one ROV following another ROV with the April tags, so we're kind of able to simulate the predator versus prey challenge there as well.
Yeah, so here's our Instagram winning picture. So we won the best posing team. And then you can scan the QR code here to see the Instagram post.
I appreciate that.
Thank you.
As a social media coordinator for this program.
Thank you for the post. And then here's our contact information. Most of us have our LinkedIn page, and then Saruth and Keshav, they have their personal website. You can scan the QR code to contact us.
All right. To wrap it all up, I'd like to thank BWSI for being such a great program. It was really transformational. I also want to thank all the mentors. So we had 3 TAs and Dr. Saad as our great teacher. Come on. Okay. So Dr. Saad, he was a really great professor. He taught us a lot. And in addition, we had 3 great TAs. We had Max, Vincent, and Asjad, and they were always there, and they always helped us debug even when we didn't just read the manual. Good. So yeah, now we're, if anyone has any questions, you can ask them.
Thank you for that really informative presentation you guys gave us. I think that really illustrated your experiences over the past 4 weeks. My final question before I release you back to our live audience here is, what was your personal highlight from the past 4 weeks?
I think my personal highlight was when on the last day when we were testing our AUVs in the pool, the April tag detection finally worked, and we were actually able to follow the April tag all the way down the length of the pool. And I think it was really just rewarding seeing all of our weeks of hard work go and end up in a final algorithm that actually worked in the real world.
I think for me, there are like multiple moments in the program. Like, although we learned a lot of stuff, one thing I also really appreciate the program is like the people that are in it and all of the stuff that we did together. Like in the beginning, we had a lot of like fun with like the drawing game where you like draw on someone else's back and then on the whiteboard. And there's just like a lot of fun moments, especially with my group. We were basically just working together nonstop for basically 2 weeks to get to this point. So honestly, the whole process was just really fun, and there wasn't like a specific moment for me.
Yeah, and I think for me, I really had like many personal highlights. As like what Vismay mentioned, we won the posing picture award, and then we also, I mean, for me, my personal highlights was actually from the first 2 weeks, where I was like doing all the crazy integrations on the chalkboard. I mean, I was definitely overcomplicating the problem because Dr. Sa just asked me to solve a very easy physics problem, but then I used integration, and I actually found the area to be divergent, and then that was just so fun. And then, but yeah, in the end, I think it was just very rewarding to see that how far we've came through like after all the challenges, and it's just really transformational.
I think the biggest thing for me was every single time we found an error, it would always just be something really something we could have fixed beforehand. So I think something I would like to take away is a learning experience, and that's just to always try and check your code before you go and test. So that was, I think that's we could have cut down a lot of time, and I feel like the highlight was when we were at the final day, we were finally testing with the other team, and it was just such a mind-boggling moment when we saw that we actually followed the other ROV. It was just so cool to see.
I think the highlight for me would be every Friday when we went out, like our entire, almost everyone in the AUV class went out, and we went to go eat food from everywhere. We went to go eat Korean food, went to eat Vietnamese food, and a bunch of other stuff. And then another, like I guess a sub part of the highlight was walking home on a Friday with Josh in a thunderstorm. So yeah, that was fun.
Thank you so much for sharing your guys' experience with this program. We're all very much proud of how you persevered for the past 4 weeks. I just wanted to say congratulations for making it to the final event, and I hope you enjoy the rest of your day.
So the plan was to calculate the forces applied in the robot frame, to use those robot frame forces to calculate the net force, and to find acceleration using the equation acceleration equals force divided by mass. And we can integrate acceleration for velocity and integrate velocity for position using these physics, which Swati will explain.
Yeah. So with this problem, we have to calculate our linear acceleration. So it's a little difficult, especially since our robot is tilted like this. So first we can look at all the forces applied in the robot frame. So this way we're taking out that angle theta, and we're pretty much only looking at our force vector, the angle alpha, which is the angle that our motors are tilted at. For our AUV, it's at 45 degrees, but we're just trying to generalize. So we can use trig to find out that if we use projection, the force on the x-axis would be T1 cosine alpha, and the force on the y-axis is T1 sine alpha. We can apply this to all of our 4 motors. And as you can see in the red, that's all of our forces in the y direction, and in the yellow is all of our forces in the x direction. So because this is still in the robot frame, we say that the force in the x prime direction is this equation, and the force in the fy prime direction is this equation. So now with this, we can apply our tilt to the angle theta like this. And to do this, we apply our rotational matrix. To use the rotational matrix, we have to transform these into matrices too. So we say all the forces for T1 is here, all the forces for T2, T3, T4, like this. And this is our net force. Then to find our acceleration, we can just divide this force by mass. And we implemented this into a Python function that'll do it for us. Our next problem is to find our angular acceleration on the AUV. So our plan is to take all of these equations. So for example, torque is equal to the radius times the force times sine of the theta of the angle, and this one. And we create functions, and then we use those to find the angular acceleration. So these are our functions. And we did a bit more math to find the torque and in 2D rotation. So you can see it right here. And we end up with the equation that the torque of T1 is equal to T1 times the length times sine times the length again times cosine alpha. And since our alpha is the same for all of these, we can say that the torque of T1 is equal to the negative torque of T2. And then we can add these all up and put it all together in one Python function. Then we can just calculate the angular acceleration by dividing by mass. And then lastly, we had to simulate the AUV motion. So we combined both linear and angular acceleration. So you input the t, which is all the force vectors, alpha, the angle, the length, the width, all the rest. And then with this, then you return the time. You get the x position, the y position, the velocity, the angles, and acceleration. And next, we simulated this AUV motion, which Ty will explain.
So after understanding how the forces apply, like how the motors apply forces onto the AUV, we plug in a certain amount of forces onto each of the motors and created the simulation. And in this simulation over here, we are trying to draw a flower. And so that's what we did for the physics part. And because we are trying to let the AUV to be driving autonomously, we have to use the PID control system over here. So the PID control system takes in the error, which is going to be the difference between the desired set points and the current set points, and then plug it into the system over here. And not only the autonomous underwater vehicle uses this system, like the race car also uses it because they have to detect the lines in order to follow it through the lanes. And in our case, we use this system to control the depth and the heading of the robot. And to do so, we plug in the error into and get the proportional gain, integral gain, and derivative gain, and sum it together to get the outcome. And then we repeat the process all over again until it reaches the desired set points. So this is our code for the depth control. As you can see in the video, our robot is maintaining at the same depth in the pool without like floating all the way up to the surface of the pool or going all the way down to the bottom of the pool. And the heading control allows the user to input a desired degree into the function and then let the AUV be facing the degree that the user have implemented. And then after that, we use the heading control and the depth control into other functions like the lane detection, lane following, and April tag control, which is going to be mentioned later in the presentation.
So next we did lane detection and lane following. So for lane detection, first we detected all the lines. We did this by applying a certain set of filters. So we would apply Gaussian blur, turn it to black and white or grayscale. This way we can see all the lines. And in this, we had some issues with our threshold values. So basically, sometimes it would be detecting way too many lines. Sometimes it would detect not enough lines. And then once we got the right values, we made equations for all of these lines. And then we looked at which lines were closest together. And we determined those as lanes. And the ones that were further apart were not. After we found our lanes, we then found the lane center, so the line that runs straight through here. That way the AUV can adjust its heading so it can follow that line. So we have a video that shows our AUV detecting a lane and going towards it. Yeah. And then next we have April tags. So you can see our AUV is following something called an April tag. So this basically is like a standard type of tag where the robot camera can detect the center of this tag and compare it to the center of the camera image. This way it can find the distance and so it can adjust the robot so it can be centered with it. So you can see on this image, we have a little cross where the center of our camera is, and we have the center of the April tag, and these values below show the distance and the error. All right, and now we have a demo by Amanda.
Okay. So I tried getting it to go to my webcam, but that didn't work. So we directly plugged in the Raspberry Pi. So now it kind of works. Do you have the April tags? Think of the demo. So if we were in water, theoretically it would move towards either the April tag first. If there were no April tags, it would move along the lanes. It would redirect itself to move along the lanes. So here's a demo of the April tag in action, actually. Yeah, I can see. Right. That lane detected, that's gonna be the lanes. So these are marks along the ground. And then if I put an April tag in, it should say April tag detected. Yes. Yeah. So. Yeah. Mhm. Yeah, we'd use that, and then we'd readjust the PID, that control that she was talking about, to actually move towards either the April tag or the lanes. Yeah, thank you.
So that was a very detailed and informative presentation, guys. My last question before I release you back to our live audience here is, what was your personal highlight from the past 4 weeks? You have anything to share? Here goes.
I think I really enjoyed like learning a lot. Like I've never taken a physics class, but then after this, like I just like am more exposed to like the wonderful world of physics, and I want to learn more.
I think the moment for me is when we put the robot into the water and it actually floats onto the water instead of like sinking. Yeah.
I really enjoyed like just being around people that like shared the same interests as me, and also being able to just sort of basically have like two of my like main passions combined. Like I like anything marine, and I also like robotics.
Okay, yeah, so there's a lot. I like the Draper field trip, the field trip that we did down to the MIT Sailing Pavilion, and then, yeah, there's that. And then Dr. Sata, like she said, I didn't take a physics class before this, but I feel like I have a better grasp of those concepts now that I've taken this. Yeah.
Awesome. Thank you so much for sharing, you guys. We're all very proud of what you've accomplished in the past 4 weeks. You should be proud as well. I'm sure you know. I'm sure you are. And thank you for being here and making it to the final event. Thank you so much.